Hi, I'm Caelyn Hirschman, and today I'm going to be speaking about the effects of joint quasi-stiffness on leg stiffness when running on slopes. The level ground running is well described by the spring mass model. Here the body is a point mass and the legs are massless linear springs. Leg stiffness is the quotient of peak vertical force and leg displacement. Leg stiffness adjusts to accommodate changes in running speed and slope. The spring mass model, however, assumes that the center of mass vertical position at touchdown and toe off are equal. This is not true for slopes, and means that leg stiffness before mid-stance, or initial stiffness, and leg stiffness after mid-stance, or final stiffness, may be different. The ankle or knee can also be characterized as springs, but with angular stiffness. During level ground running, joint stiffness is modified to increase speed and relates to increased leg stiffness. Understanding how leg stiffness and joint stiffness change on slopes in biological legs could help to inform the design of assistive devices. Running-specific prostheses, for example, are designed to act like the leg spring during level ground running, but we don't currently know whether this works the same way on slopes. We therefore aim to determine the contribution of joint stiffness to leg stiffness during sloped running. We calculated ankle, knee and hip stiffness and theoretical leg stiffness using a novel equation. We hypothesized that when running uphill, final ankle stiffness and final hip stiffness will contribute more to theoretical leg stiffness, and that when running downhill, initial knee stiffness will contribute more to theoretical leg stiffness. So 20 runners ran on a forced treadmill at positive 6 degrees at 2 meters per second and 0 and negative 6 degrees at 3 meters per second. We measured ground reaction forces at 1000 Hz and lower body motion at 200 Hz. We calculated joint angles and moments during ground contact using Visual 3D. So this graph is a work loop at the ankle, but its main purpose is to explain how we split up joint stiffness into initial and final values. So angle is on the x-axis and moment on the y. And initial joint stiffness is the slope of the line from 20% of maximum moment to maximum moment. And final joint stiffness is the slope of the line from maximum moment back down to 20% of maximum moment. Now to determine how joint stiffness affects leg stiffness, we used an equation derived by Nitt and Molcar to calculate initial and final theoretical leg stiffness. So to calculate initial leg stiffness, we inputted initial joint stiffness values at the ankle, knee and hip, as well as the average external moment arm prior to mid-stance at those joints. And to calculate final theoretical leg stiffness, we inputted final joint stiffness values at the ankle, knee and hip, as well as the average external moment arm after mid-stance. So let's hop into some results now. We're going to start off with theoretical leg stiffness. These loops display data from a representative subject. We have leg displacement on the x-axis and vertical ground reaction force on the y. The arrow indicates the direction net mechanical work and the star indicates foot contact. For this graph and all of the following, red is going to be 0 degrees, blue positive 6 degrees and green negative 6 degrees. Currently we have theoretical, initial and final leg stiffness values on the graph for 0 degrees. We can see that at positive 6 degrees, initial theoretical leg stiffness decreases when compared to 0, and at negative 6 degrees, final theoretical leg stiffness increases when compared to 0. This next graph displays work loops at the ankle. So we have angle on the x-axis and moment on the y-axis. The angle measured at the ankle is depicted on the figure on the right. So we currently have 0 degree initial and final ankle stiffness on the graph. When I bring in the positive 6 degree loop, we see no significant difference in initial or final stiffness when compared to 0. And at negative 6, similarly, we see no significant difference when compared to 0. So moving on to the knee now. Again, we have angle on the x-axis and moment on the y-axis. At positive 6 degrees, we see an increase in initial knee stiffness when compared to 0. And at negative 6 degrees, we see an increase in final knee stiffness when compared to 0. So last but not least is the hip. Angle on the x, moment on the y. At positive 6 degrees, we see an increase in final hip stiffness when compared to 0. And at negative 6 degrees, we don't see any significant difference in initial or final hip stiffness when compared to 0. So this graph really aims to get at the question of how are these individual joints contributing to overall theoretical leg stiffness. So we have average joint stiffness on the x-axis as a percent and phase of stance for 3 slopes on the y-axis and each joint across the top. The 100% on the x-axis equals the sum of the joint stiffness values at the ankle, knee and hip that I just presented on the graphs, and of the values that were entered into the theoretical leg stiffness equation for each slope. The current bars on the graph represent ankle stiffness. We did not see a significant difference in the contribution of ankle stiffness to theoretical leg stiffness across slopes. When I add the knee in, we can see that at -6 degrees, final knee stiffness contributed to theoretical leg stiffness 15% more when compared to 0. And for the hip, we found that at +6 degrees, final hip stiffness contributed to theoretical leg stiffness 15% more when compared to 0. So swinging it back around to the hypotheses, we can partially accept our first hypothesis, as final hip stiffness did contribute more to theoretical leg stiffness when running uphill, but we reject our second hypothesis because it was final knee stiffness that contributed more to theoretical leg stiffness. So in conclusion, we found that when running uphill compared to level ground, initial theoretical leg stiffness decreased and final hip stiffness increased. This means that an assistive device may need to be less stiff initially and more stiff after mid-stance, but only at the hip. We also found that when running downhill compared to level ground, final theoretical leg stiffness increased and final knee stiffness also increased. This could mean that an assisted device needs to have increased stiffness after mid-stance at the knee. Future directions of this work include analysing calculated leg stiffness, as well as doing all of these analyses on more speeds and slopes, as well as investigating further the implications that these results have on device design. So thank you so much for listening. I'll be here virtually to answer any questions.